So one potential shortcut that holds promise is to try to identify a biomarker. This could be a blood test that is what we call a surrogate or a substitute for a clinical endpoint. So if you're looking for biomarkers, the question you have to say is you want to find something that's different in NPC kids versus kids that don't have NPC. But you have to ask, is what you're looking at a surrogate or a substitute for a clinical endpoint? And it's actually very difficult to prove that, and it's a process that takes time to prove that, but it's one, identifying them is the first step in the process. And that process of showing that it's a surrogate is referred to as either validation or evaluation. Okay. Does the biomarker ascertain a therapeutic effect? I mean, that's what we want it to be. We want to measure it, and if this moves in the correct direction, ultimately it says we're going to have a positive clinical impact. But you could do a therapeutic intervention that could either have beneficial or harmful effects that this biomarker doesn't respond to. Or you can do a therapeutic intervention, and unfortunately there's a lot of examples of these in the medical literature, where the biomarker changes in a way you think might be positive, but ultimately there's no clinical effect. So just identifying a biomarker isn't enough. You need to start to study it, and you need to look how it actually behaves in patients and how it behaves in response to potential therapeutic interventions. Ultimately, we would love to identify a biomarker that's actually related to pathogenesis. That this is some protein, and Dr. Liscombe talked about, TNF, an inflammatory mediator. Well, if you looked at it, that could be a biomeasure, it could be a biomarker. But it also has biological effects in that it increases inflammation. So those are biomarkers that you would really like to identify, because not only by reducing them do you know you're doing something positive, but you're also intervening in one of the pathological aspects of the disease. Okay, so one of the groups of biomarkers that we have identified are biomarkers that are related to this oxidative stress. Dr. already talked about that briefly. There's one of the downstream pathological processes is that there's increased oxidative stress in NPC, and that's been shown in cell culture. It's been shown in the mouse model. And we started looking into kids. Was there evidence for oxidative stress? And we were really looking at two classes of markers. Markers that we think are specific for NPC, so are reflective of oxidative stress in NPC patients, and then markers that are really non-specific, that if you have oxidative stress for any reason, would change. One of the specific markers, and Dr. Ori is going to talk about this in the next talk, is that we found increased levels of oxysterols in the NPC patients. So I'm not going to touch on that more other than just say that it's there. And this is likely a disease-specific marker of oxidative stress in NPC. And this is a graph that a Mac does not like. One of the non-specific markers of oxidative stress is looking at coenzyme Q10. Coenzyme Q10 is a molecule that cycles between an oxidized form and a reduced form. And what we found is when you look at the levels of coenzyme Q10 present in the NPC kids and young adults, the levels are fine, but the amount of reduced coenzyme Q10 is decreased. It's as if it's not cycling the way it should. Another non-specific marker that we look at is something called Trilox equivalent antioxidant capacity. So it's a way of looking. There are a lot of antioxidants in the blood. Coenzyme Q is one of them. Vitamin C, vitamin E are all antioxidants. You have blueberries, which have some other antioxidants that come into your blood. This just tries to compare the total antioxidant capacity that's in the blood at the time you draw that blood. And compares it to a molecule, reference molecule called Trilox. And what you can see, this is the numbers we have now are higher, so this is an older group, but the results are the same. When you look at kids, and we actually, with the help of Hadley Hope Foundation, collected blood from age-appropriate kids that don't have NPC. You can see that the antioxidant capacity in the control kids is higher than the age-matched antioxidant capacity in NPC kids. So two non-specific markers and then a disease-specific marker that all suggest that there's increased oxidative stress. So you're not relying on just one test. It's a group of tests that suggest we have a problem. And that's consistent with the basic science studies that we've done. So how do we take this idea and think about developing a therapy for it? So you have this intracellular cholesterol lipid accumulation that you all know about. There's a black box in here. And you end up with increased oxidative stress. The inflammation may be wrapped up in here, but there may be many processes. The cells are sick, so they're not able to deal with oxygen the way they should. The combination of this, our hypothesis is the combination of this increase of cholesterol combined with oxidative stress, which is very relatively specific for NPC, leads to this disease-specific increase in oxysterols. The oxidative stress, which can be found, is found in NPC, but as well in other disorders, leads to non-specific ones, in part reduction of coenzyme Q, so you have an alteration in the ratio, and decrease in total antioxidant capacity. So this sort of is a hypothesis to explain our results. How do you intervene in this process? And obviously, there's a lot in the news about giving antioxidants. And so you could say, I want to give antioxidant to correct it. Or you could say, I want to give reduced coenzyme Q to correct it. But, it's an issue, I think, recycling. But by giving antioxidants, you could try to correct these endpoints. Or you could try to use the body's own system. And one of the major molecules in cells that the cells use to fight oxidative stress is a molecule called glutathione. And it's a sulfur-containing compound that the cells can use to help fight increased oxidative stress in the cells. Now, you can't give glutathione itself because it doesn't cross cell membranes. If you give it, it's not even going to be absorbed. But there's a drug, and we refer to it as a prodrug, N-acetylcysteine. When you take N-acetylcysteine, it's first converted to an amino acid called